My name is Gustavo, and the idea of my presentation is to explain how the algorithm to convert from concentration values obtained from the Elgas boxes to risk evaluation. So for that case, we are going to show an example, a typical case of measurement from a chip. This is the situation we have normally. Sometimes even more parameters when collecting several parameters at the same time, and sometimes more than this one that I'm showing. So you can imagine that this can get complicated for a normal user to understand the information they are receiving. We see from this data, for example, we see different environmental parameters. We can see peaks, we see fluctuations. So that means that there is important information that we would like to know, but we don't know how relevant or meaningful this information is for the user, how harmful this concentration we are obtaining is for the user. So the idea normally what normally is done in these cases is to compare the concentration values with thresholds. So let's say an example like this. This is the PM10. Let's say we have different thresholds. There exist different thresholds for non-occupational or occupational, and depending on how close the concentration are for these thresholds, you can say how in danger or how harmful is the environment for your health. But so we collected several thresholds for different literature, the different legislations, and from different countries and organizations, and we tried to put all those thresholds together for the parameters we were analyzing, and this is the table I'm showing here. So still, this type of visualization can be complicated for a typical user when you are obtaining a lot of data from different parameters. At the same time, this kind of information can be tricky for the user to act fast in certain situations, or to make a mental idea of what is the real situation, that is happening. So for that reason, we try to create to harmonize or to standardize all these concentration values into one level of risk. So for that reason, we create this piecewise function for each parameter, and with this function we can transform for the actual concentration for the parameters we're measuring into a level of risk. And the nodes that define this piecewise function are the thresholds we collected from the different legislations. And the risk will be higher depending on the concentration value. If you get a higher concentration value, you will have a higher level of risk. And another thing that might happen, as was already mentioned, is that it might be possible that the person that is exposed to the environment can be a person that is an occupational personnel, or a worker, let's say, or a person that is not a worker, and the legislation says different state different thresholds depending on you're a worker or not. So for that reason, you use the same piecewise function, but we superpose a color scale depending on whether you're occupational or not occupational. For example, in the left figure, top figure, we see the piecewise function for the PM10, and we can see a superposed color scale from blue to red, and depending on the level of risk, you will get a value of the risk and a color depending on how in danger or how harmful the environment is. In the case of the non-occupational, you use the same function, but we change the interpretation by changing the color scale. So you will get an earlier red color for lower concentrations in the case of the non-occupational. And below we see the actual concentration for both cases of PM10, and how for the same environment you get more blue for the non-occupational than for the occupational, that you get more red in the peaks. So what's next slide? I show a real example using the data you see previously. You can see the actual concentration during the full measuring campaign with the color scale superposed to that concentration. And now you can see that it's easier for a user to identify where their health is more harmful, is more in danger, or how is their actual quality, or how in danger they are. And for example, we can say for ozone, let's say, you see in the right top, in the left top, you see that they have more blue colors, and for the non-occupational, you see that the peaks contain more red colors. So that means that the risk is higher for non-occupational person exposed to the same environment. At the same time, you can really notice that let's say the NO and SO2 is not the concentration we obtain is not meaningful, because for both contexts we obtain a very low value of risk. It's blue for during the full measuring campaign, so it's not relevant data we can dismiss. And so this is the case of the concentration for the individual risk. But still, you can see that there is a lot of information to process. We have to evaluate individually each parameter to get an information on how the environment is. So for that reason, we wanted to simplify more the information, and we calculated an overall risk using the following formula. This formula is used to give an interpretation of the combination of each individual risk at any given time. And below you can see the compressed information for all the parameters for the non-occupational, on top of all the occupational context, and below for the non-occupational. And you can see for the same environment, the occupational context is the air quality, or the risk is lower than for the non-occupational person exposed to the same environment. And so this is the summary. The summary is that we were able to convert from complex information for multiple parameters into one single risk assessment, and this way to make the information more actionable and make user easier to understand and give an interpretation to the actual environment they are exposed. Yeah, that is all I have to say.